Stable matching and faster bipartite matching. Recap of previous lecture, we have discussed weighted bipartite matching, transversal equality subgraph and Hungarian algorithm. Before this particular lecture, we have also covered the maximum bipartite matching. Content of this lecture, in this lecture we will discuss stable matching, then we will take up the algorithm for it, that is given by Gale and Shapley algorithm. We will discuss also advanced topic on maximum cardinality bipartite matching and another algorithm for it, that is called faster bipartite matching, and this algorithm is also well known as Hopcroft-Karp algorithm. Stable matchings. So, instead of optimizing total weights for a matching, we may also try to optimize using preferences. Hence, the matchings which are based on the preferences optimizations are called stable matching. For example, if there are n men and n women and we want to establish n stable marriages, then this is an ideal solution, that is called stable matchings. Now, if a man X and a woman A are paired with the other partners, but X prefers A and to his current partner and A prefers X to her current partner, then they may leave their current partners and A prefers X to her current partner, then they might leave their current partners and switch to each other. In this scenario, we say that the unmatched pair XA is an unstable pair. Let us take an example to understand this concept of unstable pair. So, here we are given a pair AY and BX, and we say that this particular pair is unstable if A prefers X and B prefers Y, then this particular pair will become unstable. Or we can also say that if A prefers X and X also prefers A, then this particular pair will be unstable pair. So, that is shown here in this particular example, that is for A prefers X in compared to Y. Similarly, for X prefers A in compared to B. So, if a pairing AY and BX is given, then this is an unstable pair. So, having shown what is an unstable pair, now we define a stable matching. A perfect matching is a stable matching if it yields no unstable unmatched pairs. So, unstable unmatched pairs, in the sense the matched pairs are unstable, hence they are called unstable matched pairs. That means the current pairs will basically prefer each other which are not in the current pairing. So, another example which we will give you is about, let us say that we are given men's XY ZW and woman ABCD, and in this particular problem setting we are also given the preferences of the other mates, other partners for all the other partners. For example, X will give a preferences for A, B, C, D. For example, here we will say that X gives a higher preference to A is greater than B is greater than C greater than D. Similarly, Y also gives a preferences in this particular ranking or order, that is Y prefers A is greater than C is greater than B is greater than D. Similarly, Z and W. On the other side also, in this particular problem setting, that is woman also has to give the ranking of their preferences for all the men which are listed. For example, A will give a preference to Z, Z is greater than X is greater than Y greater than W. Similarly, B, C and D. So, this becomes a problem setting. For stable matching. We will see now the algorithm which is well known as Gale-Shapley proposal algorithm, and which will give the stable matching as an output. So, the input of this algorithm is the preference ranking by each n men and n women. So, the graph, if we see, it will look like K and N. There is a complete bipartite graph where one partite set represents n men and another partite set will represent n women. Here the idea is to produce a stable matching using proposals by maintaining information about who has proposed to whom and who has rejected whom. There are two important notions, proposal and the rejection. The algorithm will iterate for each man proposes to the highest woman on his preference list who has not previously rejected him. So, it will start from the step number 1. Step number 2 says that if each woman receives exactly one proposal, then it will stop and use the resulting matching. Otherwise, every woman receiving more than one proposal will reject all of them except the one that is highest on her preference list. That is the third step. Every woman receiving a proposal says maybe to the most attractive proposal received. Attractive in the sense it will be on the preference list placed at the higher order. Now, all these 4 steps of this algorithm let us trace on the same example. These preference orders are in this particular manner. Now, here if we represent the first step, if we see the step number 1. So, every man will make a proposal to the highest ranked woman in his preference list. So, A will send X will send the proposal to A. Similarly, Y will send the proposal to again A. Z will send its proposal to C, and W will send the proposal to C again. So, here we can see in this particular figure that A will receive the proposal from X and Y. Similarly, C will receive the proposal from Z and W. So, step number 2, what step number 2 will do? So, the woman A, since woman has received more than one proposals, she will accept the one which is at the higher preference compared to the other one. So, it will accept X and rejects Y. So, Y will be rejected. So, A will send the rejection, and this will be the maybe condition. Similarly, here on the Z side, on the C side. So, C will accept W because it is higher rank proposal compared to Z. So, Z will be rejected here in this particular case. So, what will happen after this? So, now x and a, that is fixed, then another thing which is fixed is y and c. Let us work out here in this particular picture the entire algorithm and then we will summarize it. So, here in the iteration number 1 or the step number 1 with the first iteration, what it does is x, a has accepted x. So, this is accepted in step number 1 and also c has accepted w. So, c has accepted w and y will get a rejection. So, y will get a rejection and z will also get a rejection from c and y will get a rejection from a. Now, we will see that, so here c and a, they are being accepted. Now, let us go to the next iteration because y and z, they have got the rejections from their respective this one a and c, because there is a clash in their proposals, more than one proposals were received by a and c. So, they have to accept one and reject the other proposals. So, now the next step will be that the y will send the proposal to c, y will send the proposal to c and z will send the proposal to d. Now, since c will receive only one proposal, y will send to c. C has already So, y will send to c. C is already has higher preference. So, it will basically send the rejection. So, now y will send to b the proposal. So, b has received only one proposal. So, b will accept the proposal of y. So, y is also fixed and this will be fixed as. Similarly, as far as d is concerned, on receiving z, so d has only one proposal received. So, z will be accepted here. So, d will be basically approved here in this particular scenario. So, now with this scenario, the stable matching pairs which we will basically collect is x a, then y b, then z d, then w c. Now, here let us assume that x y z w, they are men and a b c d, they are women. So, what we will see here in this particular algorithm, that we have started looking the men. So, this particular algorithm is men optimal. If we run the algorithm keeping woman on the left side and then men on the right side, so it will be men woman oriented and woman optimal algorithm will be resultant out of Gale-Shapley algorithm. Both are not equal in this particular problem setting. So, that is why if it is a man optimal, so men, this particular algorithm will make this man happier. Similarly, if it is woman optimal, then the women will be made happier in this particular algorithm. So, all these steps are basically traced up. Now, we will see another example of a stable matching algorithm. Let us see that the preferences of 1 is 2 and the preference of 2 is 3, preference of 3 is 2, then preference of 4 is 4. So, here in this case 4 is receiving only one proposal. So, 4 will accept it, the proposal from 4, and it will also be enclosed over here. Similarly, as far as 3 is concerned, 3 will receive only one proposal, that is of 2. So, from proposal 2, this particular pair will be finalized. As far as 2 is concerned, there is a conflict. So, 2 has a choice between 1 and 3. So, 3 is having higher preference. So, as far as 3 is concerned, 3 will be getting first preference, and 2 is concerned, 2 will reject the proposal by 1. So, this gets rejected. Now, in the next round, so when 1 will send to 4, as far as 4 is concerned, 4 has already sent maybe to 4, but when it receives a higher preference, then it will basically allot, or it will accept the proposal made by 1. So, this is accepted, and this particular proposal from 4 is rejected. So, if it gets rejected, then again there is a possibility that 4 will now send its proposal to 1. 1 so far has not yet accepted any proposal. So, after receiving from 4, it will send the acceptance. Hence, this particular pairing is finalized by this particular algorithm. So, whatever we have worked out is also shown here in this particular final example. Same things are happening. Now, let us analyze the Gale-Shapley algorithm. This algorithm terminates after no more than n square iterations with the stable matching as an output. So, the stable matching produced by the algorithm is always gender optimal. I have already explained this. So, each man gets the highest rank woman on his list under any stable marriage. One can obtain the woman optimal matching by making woman propose to the man. A man or woman optimal matching is unique for a given set of participant preference. The stable marriage problem has a practical application such as matching the medical school graduates with the hospital for residency training, and so on. It has many other applications in many other fields. Now, let us see more details about stable marriage particular problem. Here we can see that each man ranks woman in SW in the strict order of preferences. So, also woman ranks men in the strict order of preferences. The matching M is bijection between man and woman. So, man M prefers woman to his partner in the matching M, W prefers M to her partner in matching M. A matching that admits no blocking pair is said to be stable. Hence, Gale-Shapley stable marriage was first formalized by Gale and Shapley in 1962. The structure of the stable marriage algorithm, here we can see that the optimality property of each algorithm, man oriented stable matching, simultaneously the best possible stable matching for all men. Similarly, woman optimal, also the best possible stable matching for all women. Now, deletion that occur during the execution of either algorithm result in a set of reduced preferences list on the termination of each algorithm. Now, if you take the intersection of man oriented list and woman oriented list, then the intersection will be called as GS list. The GS list have many important structural properties, and depending upon the application, these particular properties are exploited or being utilized to solve various particular problem. Faster bipartite matching. Faster bipartite matching algorithm is given by Hopcroft-Karp algorithm in 1973. Now, this particular algorithm will find out the maximal cardinality matching faster than the algorithm which we have seen earlier in previous lecture. That is, the algorithm which we have seen was called augmenting path algorithm, APA algorithm. and that algorithm, if you recall, would take of the order n cube time in the worst case, where n is the number of elements or the nodes in the graph, in a bipartite graph. This particular algorithm, which is basically doing the same task, that is finding out the maximal cardinality bipartite matching, will find out the maximum matching a bit faster, and the total time which this particular algorithm will take to compute the maximal cardinality matching is of the order n raised power 2.5. So, hence that is why this algorithm is called a faster bipartite matching. So, this is an advanced topic. So, we are going to give you the glimpse how what basically makes this algorithm faster compared to the augmenting path algorithm. So, the running time of the algorithm for finding maximum cardinality matching in a bipartite graph can be improved by seeking the augmenting path in a clever order. When short augmenting paths are available, we needn't explore many edges to find them, and that will be done through the use of a breadth first search. So, breadth first search goes and explores the shorter path before it goes and explores the longer paths. So, hence using that particular property, breadth first search simultaneously from all unsaturated vertices of a one partite set X will find many paths of the same length in one examination of the entire edge set. Hopcroft-Karp in 1973 proved that subsequent augmentations must use longer paths using the property of the breadth first search. So, the searches can be grouped in a phases for finding paths of the same length. They combine these ideas to show that a fewer phases are needed, thus enabling the maximum matching of a bipartite graph to be found in of the order 2.5 time, that is faster than the previous one. Let us see the algorithm working, and we will then analyze the more details about the Hopcroft-Karp algorithm. So, initialize the matching set M as empty. Why? Because we have to begin it. Then we start the iterations. First, we have to build the alternating level graph rooted at unmatched vertices in L using breadth first search. Take this particular example. So, this particular problem setting, we see that L is nothing but the edges which we want to be saturating. So, let us call it as L instead of saying X. Here we are little bit changing the terminologies. Here we call it as L, and on the other side, instead of calling Y, we say that it is R. And let us say that we are given the matchings which are shown in the orange colors. So, matchings which we are now given. Definitely this is not basically the maximal matching. So, we are basically extending this particular matching in the steps. So, if we take the node number 1, the node number 1 has two paths, one will go to 2, the other one go to 4. Another node which is unsaturated by any of these matched edges is node number 3. So, 3 will go to a node number C which is also unsaturated, and node number this 8 which is also unsaturated. So, simultaneously when we invoke the algorithm, that will basically invoke from both these particular unsaturated nodes. Now, in both these nodes the BFS algorithm will run. So, after running the BFS in this particular level, 1 will reach to 2 and 4, similarly 3 will reach to 6 and 8 on the other side, it will go via the unmatched edges. Now then what it will do? It will pick up using the matched edge and it will reach again to L. So 2 can take this particular edge, matched edge, and can reach to 5. Similarly 4 can reach to 7 using matched edge. 6 will take the matched edge and can reach to 9, and 8 can take a matched edge to reach to 11, and that too in the next level of BFS. Now after reaching on L, then it has to pick the unsaturated edge and can reach to again to the R to basically touch unsaturated node, and that will be an augmenting path. Let us see that 5 has 2 options. 5 can reach to this particular node which is unsaturated. 5 can also reach to this node which is saturated. So 5 has 2 options. So it can reach to 12 or it can reach to 10. 12 is already saturated, so it is useless. Useless in the sense it is not going to identify augmenting path. This will identify augmenting path in this particular level. As far as node 3 is concerned, when it is at position 9, it can reach to node number 10 which is unsaturated. This is node number 10 which is unsaturated. Similarly, node number 11 is concerned, has only one option. By unsaturated edge it can reach to 16. Now we can see that at this particular level of inspection, this is unsaturated node, this is also unsaturated node. You can reach this unsaturated node via this path, or you can reach this particular node via another path. You can reach via this particular path. So there are 3 different possible paths, and hence they are called alternative level graph when this BFS is run parallelly simultaneously from these 2 vertices which are unsaturated. Similarly, this also node is unsaturated, so there is only one path possible, and this can be reached from node number 1. So there are, how many paths are there? 1, 2, 3, 4. 4 different alternative paths are there, but we have to find out the vertex disjoint path. So vertex disjoint path means if we select this particular path, let us assume, then the other 2 paths cannot be basically used up. Why? Because the vertices are common. So just see that only one out of them, only one path will be used up when we talk about the vertex disjoint paths. So here we are finding up an augmenting path M with a maximal set of vertex disjoint shortest length paths. Let us see the same scenario. That particular path which we have identified is also selected as the vertex disjoint shortest length path here in this particular algorithm. So once this particular path is identified, then we will extend this particular length and we will find out the other augmenting path and so on. So let us see the number of iterations. So this building of the path will require order E edges. So it has to be built through the edges. So, number of edges are to be scanned. So, hence of the order E this particular step will take. Now, this repetition, how many times it is going to repeat here, that is called the phases. So, it is proved by the Hopcroft that the total number of phases required to complete this particular matching will require only of the order n raised power or under root n, that is nothing but n raised power 0.5. Hence, this particular approach will take 2.5. Why? Because so E times multiplied by root n. So, E you know that is n square in the worst case. So, n raised power 2 times n raised power 0.5, that comes out to be n raised power 2.5 is basically the time complexity analysis of this particular algorithm. So, there is a theorem which says that given a bipartite graph Hopcroft-Karp algorithm finds a maximal cardinality matching in a time of the order E times root V, with V is the set of vertices and E is the set of edges. Conclusion: in this lecture we have discussed stable matching given by Gale-Shapley algorithm and a faster bipartite matching which is given by Hopcroft-Karp algorithm. In upcoming lectures we will discuss matching in a journal graphs and also discuss Tutt's one factor theorem, F factor of a graph, Edmonds Blossom matching algorithm for journal graphs. Thank you.